All right, welcome to the color assessment. Let me move the bunny book. All right, color assessment, last assessment of the year, here we go. Question number 1 says, which is not a primary color of light? So what are the primary colors? Well, one of the things about this that makes it difficult is that when you were in elementary school, they told you that the primary colors were red, yellow, and blue, but they were talking about the primary colors of paints. And here we're talking about the primary colors of lights. And so the primary colors of lights are green, blue, and red. Those are 3 primary colors of light, and we can make all other colors out of those 3 primary colors. In fact, if you were to drop a little bit of water on your cell phone screen, what you would notice is those are the actual colors you see. Anything else is just a combination of those. So it says which is not, so yellow is not. Two says which color of light moves the fastest through air? That's a great question. So the fastest color of light is the question. And, well, they're all colors of light, therefore they all move at the speed of light, so they all go the same speed. It turns out that the difference between them is that blue is a high frequency, small wavelength color, red is a low frequency, big wavelength color, and then green would be somewhere in the middle. But they all go at exactly the same speed. Three says, why is it that we see different colors of lights? Well, the reason we see different colors of lights Why do we see different colors? Well, if you look at this picture down here, what do you notice about these? Each of these is a different frequency. So the different frequencies gives you different colors. Now, you could also say, I suppose, that different wavelengths would also give you different colors, but normally when we say it, different frequencies give you different colors. All right, let's look at number 4. Number 4 says, when seen above the atmosphere, the sun is white. Why does it look yellow in the sky? Oh, that's a great question. So we can actually answer this question just using our red, blue, and green. So red, blue, and green together would give you white. And so if we think about, here's the sun here, and we'll say it's white, which means it's giving off blue light, red light, and green light. But when it hits the atmosphere, okay, so let's say this is the Earth here. When it hits the atmosphere, what happens is the blue gets sent in all different directions. Right? But you're here waiting for you're here on the earth waiting for the light to hit your eyeball, but the blue gets taken out, which means that when you look up at the sky, you see the red and the green coming straight at you. And what we know about color addition is when you see red and green together, they look yellow. So because the blue gets scattered in the atmosphere, we see the red and the green, and that to us appears yellow. All right, let's reset here. Hold on. All right, let's look at number 5. Number 5 says, which color combination is not correct? Okay, which color combination is not correct? Well, first one says, do red and blue give us magenta? All right, so a lot of times you see this, and you can look online for this, but it has this 3 overlapping circles. Now, I can't color this in a way that's meaningful, but if we put like the blue, we'll say this one's the blue here, and then we'll put the red one over here, and we'll put the green one down here. We actually can get the rest of the colors. So we know that green and red together will give us yellow. Green and blue together give us what we call cyan, and red and blue together give us yellow. I'm sorry, red and blue together give us magenta. And in the center here, if you put all 3 colors together, you get white. Again, this is a famous picture. Hopefully you've seen it a bunch of times this week. So let's look at our color combinations. First one says red and blue gives us magenta. That is correct. Green and magenta give us white. So here if I look at green and magenta, they give us white, because red and blue and green would give us white. So red and blue is magenta, magenta and green gives us white. That seems okay. It says yellow plus blue gives us green. Well, yellow plus blue would give us white. So that doesn't make any sense. And the last one says blue plus green gives us cyan. So in this, yellow and blue do not make green. All right. 6 says, which of the following is not a primary color of pigment? Great question. So what are the primary colors of pigment? So pigments work the opposite way that light colors do. So the primary colors of pigments are what we have here. It's cyan, magenta, and yellow. So those are the primary colors of pigments. They are the primary colors of pigments, and they're the secondary colors of light. All right, what does 7 say? 7 says, which combination for pigments is not correct? So this is pigment combinations. So the pigment combinations is actually a very interesting, it's exactly the same, only different, let's put it that way, than the light colors. So when we do this, light adds together, and the more light you put in, the lighter it gets. That's why if you put in all 3 light colors, it gives you white. Pigments actually do the opposite. They start subtracting colors out from the white, which is actually pretty interesting. All right, so let me show you what the circle looks like for this. Again, I don't have a cyan, magenta, and yellow marker, so you're going to have to just believe me here. So if we make this one yellow here, and this one's cyan, and this one is magenta, When you put them together, they start subtracting other colors from the white. So for example, yellow is white light without the blue, gives you yellow. Magenta is white light without the green, that's why it's magenta. Cyan is white light without the red. And so cyan subtracts out the red, yellow subtracts out the blue, and magenta would subtract out the green. So if yellow is subtracting out the blue and magenta is subtracting out the green, if you're minus green and minus blue, that means you would be left with red. Over here, magenta is subtracting out the green, cyan is subtracting out the yellow, so you'd be left with blue down here. And then, of course, by process of elimination, you know this one has to be green, but cyan is subtracting out the red, yellow is subtracting out the blue, and you're left with green. And here, you have yellow, which subtracts out the blue, cyan, which subtracts out the red, and magenta, which subtracts out the green, which means you'd be left with nothing. And so this here, that's the black. So the primary colors of pigments are cyan, yellow, and magenta. What was the actual question? Oh, which color combination is not correct? If you do cyan and magenta, you get blue. That is correct. Magenta and yellow gives you red. That is correct. Yellow and blue gives you white. That's not true. That would give you black. And then yellow and cyan gives you green. So yellow and blue don't give you white. If you took yellow and blue, you'd be left with black. All right, number 8. Eight basically asks, how do pigments form colors? All right. Oh, this is cute. So basically, if you look at this question, all the above are true. So it says, primary pigments absorb a primary color of light, reflecting the two others. So a primary pigment, for example, yellow, absorbs a primary color of light. Yellow absorbs the blue light, reflecting off green and red, which means that's why you see it yellow. So B says, when primary pigments are mixed, they absorb multiple primary colors of light. That's true. Yellow absorbs blue, magenta absorbs green. If you don't have blue or green, you're left with red. So that's true. C says, when three primary colors are mixed, they absorb all three primary colors of light and leave you with black. That's true. So 8, kind of a tricky question. All the above are true. All right, let's reset. Here's number 9. 9 says, what are the correct colors in a rainbow according to the minute physics and the rules of color addition? This to me is fascinating. So when we were younger, we learned Roy G. Biv. We got over this pretty quick. Roy G. Biv. Red is good. Red and yellow give you orange. That makes some sense. Green's good. Blue. What is indigo? That's a question. Not a real color. And the way we think about it, violet is like a purple color. But how could you get purple there is the question. So this doesn't really make any sense. According to the Minute Physics video, we have red, yellow, that looks pretty good. Red and yellow together could give you orange, and then yellow fades into orange because you have some blue here, so this makes some sense. But what is this blue here? Right? This blue here isn't, I mean, blue is so nondescript. And so really this next color here is like cyan, and then this is blue out here. So this is red, orange, yellow, green, cyan, and blue. So, because blue and green would give you cyan, red and orange would give you, or red and yellow would give you orange, and green's in the middle. And then, so this makes much more sense. And this is actually what you really see in a rainbow. So next time you look at a rainbow, and this blue, as it gets darker and darker, can look more and more and more purple. But the only way you could get purple would be to put blue and red together, and blue and red are on opposite sides of the rainbow. And number 10 says, which of the thought is true about how our eyes work so that we perceive color? All right, 10. How do our eyes work? Well, the thing about our eyes is that in the back of our eyes we have two things. We have rods and we have cones. The rods are for, so a lot of times you'll hear it said rods are for black and white, but this is really for more light intensity. So it's like how bright things are. But the cones, there are 3 cones. Guess what? There are 3 cones, and they are a red cone, you guessed it, a green cone, and a blue cone. And as the light hits our eyes, it stimulates 1 or 2 or all 3 of these, and we perceive these as they fire to be the different colors based upon the different frequencies of light. So it says there are only 3 types of cones on our retina, 1 for each primary color. And that is the color assessment. Hope this helps.